So matrices were added to the Step 2 curriculum in 2019, and since then they seem to have asked one matrice question every single paper. So I thought I would just go through those nice and slowly, one by one. So this is question 8 of 2019. Let's get into it. We have a function which inputs 2 by 2 matrices and spits out just a random number, a real number. So this function is very much like the determinant of a matrix, like the determinant, right? Because the determinant, you give the determinant a 2 by 2 matrix, and it just gives you back a number, right? So this is acting in the same way. That's just what this is. This function also has the property that f of mn equals f of m times f of n, and we're only going to be looking at 2 by 2 matrices, thankfully, here. Now we're given a matrix M such that f of m is not 0, and I is the 2 by 2 matrix. That's of course 1, 0, 0, 1. And by considering f of mi, show that f of I is 1. So, okay, well, f of mi is, by the rule, just f of m times f of I. But it's also, well, mi is just m, right? So that's also f of m. So we have f of m equals f of m, f of I. But f of m isn't 0, so we can divide both sides of this by f of m and get f of I is 1. So that's all that done. Nice little warm-up. J is this matrix here. By considering j squared, okay, well, let's just do that very quickly. J squared is this times this. If you do some multiplying out, you end up with the identity, which is pretty convenient. Now evaluate f of j. So what we'll do is we'll consider f of j squared, because by the rule, that's f of j times f of j. But f of j squared is just I. So this is equal to f of I, which is 1, as we showed in the previous part, which means 1 is f of j times f of j, which is f of j squared. And something squared equals 1, well, the only answer to that is plus or minus 1. But we're told it's not 1, so therefore f of j is minus 1. Now, using j somehow, let's figure out these rules here, which are quite interesting. So it's like if we flip the a and the b and the c and d over, it just makes a minus of the function. And then if we swap them over like diagonally, it just has the same number it did before. Kind of interesting. Okay, so this took a little while for me to work out, but I started on the left-hand side with this. And now j squared being I is the key thing here. So I tried timesing this by j squared on the right, didn't rotate in the right way. So then I times by j squared on the left, right? F of this is the same as f of this because j squared is just I, and I times this matrix is just this matrix. So therefore, it's just, I haven't done anything. That's fine. However, I could also say j squared is this times itself. And now if I ignore the front one for a second and just multiply those two together, 0 times a and then 1 times c gives me c as the first term, and then keep going and you get this. But now I can say, well, here's two matrices in an F. Using the original rule for F, I can split that up into two things. And this one, by definition, is minus 1. So this makes minus this thing here, which is the second line. And then if I just do it again, I can eventually get to here as well. So if I now multiply that, and now putting j squared on the right does work out quite well. Again, put it on the right because j squared is just I haven't done anything here, but j squared is this times itself. Multiply those two first together to get this, because C and then D, so you just get 1D and then all the others. And now break the F up, and now this one here donates another minus 1 because f of this is minus 1, and you flip that to negative to get that there. And we're all done with this. Now this next part took me a little while to work out because I forgot the golden rule of step. So K is a matrix that looks a bit like this. Now A is a matrix such that the second row is some multiple of the first row. Now, a really good idea sometimes is just to consider the simplest cases you can. The simplest case of this happening is just when it's a matrix of the form ABAB, where the multiple is just 1. Right, this is the simplest case. And now this is where you need to remember the golden rule of step, which is you never throw away anything that they've currently got you to do so far. So this thing here is not sitting here just for fun. It's sitting here because look at the first two bits. If you swap the top row and the second row, that just makes minus f of what you had before. So if we swap a and b with a and b, that should give us minus f of a. So therefore f of a is equal to minus f of a because swapping these rows does nothing. And therefore in this case, where the multiple is just 1, f of a is definitely 0. And now that we know this, maybe we can be helped out with the bigger case, where maybe a prime, a more general case where the multiple is just some number k. But notice now, using this matrix here, that a prime is just k times a, I think. Right? If we multiply these, we get a and nothing, and then b and nothing, and then nothing and ka and nothing and kb. So this is fine, but if that means, of course, that f of a dashed is equal to f of this, f of that. I mean, it's f of this, of course, because that multiplies to make a prime. But then it's f of this, f of that. But f of this is 0. We showed that in our simple case. So therefore, f of a prime is also 0. So cool. Excellent. Very last part, let p equal this by considering all this. So we're going to pick up 3 marks here. This is fantastic. 3 marks for working out p squared, which is this. 3 marks for working out p inverse. It took me actually a second. I sat here for 2 seconds working out how to work out p inverse before I remembered that I know how to do A-level maths. So p inverse is just 1 over 1. The determinant is just 1 minus 0. So 1 over 1. Flip these 2 over, which doesn't do anything. Make those negative, and you get this. So that took me a hot second to remember that I knew how to do. Anyway, k, of course, is this. We saw it before. So, okay, now k inverse pk. I need k inverse, right, I guess. So determinant is k minus 0, so that's just 1 over k there. Swap those over, make those negative, you get this. I decided to write it like this. So now k inverse pk, so that's going to be this times that. We have to go left to right, of course. Let's multiply those 2 together first. We get this. And then we can multiply these 2 together to get this. And that's interesting because there's something else on the screen that looks a lot like this, which is this one here. If k was 2, then k inverse pk, if little k was 2, k inverse pk is just p squared. And that's got to be relevant, right? So now let's consider f of these things. Let's consider f of this. Now, the mark scheme was very clear. You weren't allowed to just say that this equals f of this, f of that, f of that. You had to consider that to be one matrix and split the f into 2 like this. And then you can split it into another 2 like this. It was just very clear that you had to do that, which was interesting. Anyway, now let's think about f of k inverse. Because we know that f of k times k inverse in singles like this is f of k times f of k inverse. But it's also f of I, because k times k inverse by definition is I, which we know to be 1. So therefore, f of k is equal to 1 over f of k inverse, or vice versa. So I can replace this guy here with just 1 over f of k, which will cancel because, of course, these are just numbers now, to make f of p. However, if little k was 2, this whole thing is p squared. So that equals f of p squared, which is f of p, which is f of p all squared. So therefore, running my equality all the way along like this, f of p all squared equals f of p. There's only 2 times that ever happens for a number, because remember, f of p is just a number. 0 squared is 0, 1 squared is 1. Those are the only 2 times. So f of p is either 0 or 1. Which one is it? Well, what we can argue here is that using this p inverse, we haven't actually used p inverse. They asked you to work it out, and then we didn't use it. Dead giveaway that we should have used it at some point. Now we can use it because we can consider f of p inverse, which is, of course, f of p inverse by the rule. But it's also f of I, which is 1. So therefore, we have this, which is very similar to the case we looked at before. However, the idea that we need to say here is, if f of p was 0, then this wouldn't work, because f of p inverse couldn't be anything. Nothing times 0 is 1. And f always takes a matrix, and it always gives you out a real number. That's what it said in the very first line. So therefore, f of p can't be 0. It must be 1. And that is the only answer that we'll get. And that was that question. Thank you for watching.